very privileged to have Charla Lambert with us today.
Yeah.
She is the program manager for science and training in the meetings and courses department at the lab. And that department runs and organizes more than 25 scientific meetings and nearly 30 short courses every calendar year. And if you recall, I sent you a link to one of those courses that she's doing in the fall, in November, the Genome Access course, right? You may want to look at that website and see all the topics that she's going to cover.
Can I ask a quick question?
Absolutely.
How quickly will that fill up? Like imminently, or do we have to?
The September course is already filled up. That's the one that we're holding. November is still open, so we've got probably about 20, 25 slots left still.
Okay.
So
they anticipated going.
They've been filling up about 3 months ahead of time.
Okay.
Yeah.
No.
Okay. She did her Ph.D. in the University of Washington Genome Sciences Department in Seattle. And she studied human population genetics, specifically computational methods for analyzing patterns of variation in DNA sequence and inferring the effects of both demography and natural selection. And then she did this, she did a postdoc, NIH, and the acronym is IRACDA. I've never heard of that before, but it's a
Not
program.
many people have.
No, it's a program that stands for Institutional Research and Academic Career Development Award, which combines a traditional research postdoc experience with teaching opportunities at minority-serving institutions. So that was very cool. And she did this in the University of Pennsylvania. And then, which is really interesting to me and some other people who have run some programs that she's going to talk about, before her current career, she calls it as a pretend biologist. She worked for a company called MathSoft. And that's the company that developed S+. Who's used S+ before? I did, and it was a little tough to use.
I know, back in the day, way back in the day.
You had to pay a lot of money for it. So now, that was the commercial precursor to this freely available R computing environment.
That's right.
But she's going to help us get through today. So it's going to be a little journey. She's going to get us through it. Charla,
something.
Thanks for coming.
All right, thanks so much, Mona. And thanks to you all for having me here. So first of all, did anybody not get a copy of slides, and or did anybody get multiple copies of slides? Did they make it all the way over there? They made it to here. Okay. Yes, I think I budgeted too few.
That's all right. We'll get some more.
Okay. So those are just a copy of the slides. I'm basically going to be going back and forth between slides and our studio. Since I've heard you guys actually have access to our studio, it's a really good way to enter into the R environment. And then I also have a couple of other handouts at the beginning of this time slot today, after I go through just a little bit of kind of historical material. We'll do a very, very basic R workshop, so introduction to syntax, what it's all about, not necessarily focused on bioinformatics at all. So the idea being that if you generate a bunch of RNA-Seq data and you're interested in putting commands together to analyze that one data set, then you'll probably be a little bit bored. If you're interested in actually learning more about R, the stuff at the beginning will serve you well because it's an unusual language and environment if you don't have prior experience either typing commands at the Unix shell or any sort of programming language like Python or Perl or anything like that. So it's a little weird to get used to. The upside is that after a somewhat steep learning curve, it's totally worth it because there are a lot of things that you can do in R. So a lot of things you can do in R that you can automate in R that you can't necessarily automate in Excel. A lot of data sets that you can handle in R that are too big to handle in Excel. And then, as you'll see later today, a lot of really, really nice user-contributed tools specifically for bioinformatics, so that if you're interested in doing something else besides RNA-Seq, depending on what your interests are, either educational or research, then you'll be able to do that. Okay, so that's kind of the outline for today. Just a quick introduction, and then I'll hand out what I'm calling the Basic R workshop, and you'll be able to type along with some commands as I'm typing them in your instance of RStudio. And then maybe after a break, we'll come back for the advanced workshop. And what I'm going to do there is have you guys download an example data set so that everybody's working on the same set of data. It's data output from CuffDiff, so I understand that that's what a lot of you are actually interested in and sort of the point that you're in this workshop. And then we'll go through some really basic commands in a really nice protocol paper for analyzing RNA-Seq data. And so we'll be pattern matching the commands that are in that protocol paper. You'll have a couple of references to take with you in order to do some more advanced stuff, or just to sort of dig in and get yourself more familiar with it after our very, very brief, fast 3-hour introduction today. Okay, so I just put some quotes up here to give you an idea. So it's R is a language and environment for statistical computing and graphics. So when people think of R, those are the two big areas that they think of using it for. Making really cool graphics and doing all sorts of exploratory data analysis, and then doing kind of sophisticated number crunching, whether it's very basic summary statistics on up to really sophisticated statistical models. So a lot of the stuff is built in. The other thing about it is that it is kind of a self-contained programming language on its own. So that's the thing that is a little hard to get used to initially, is that you have to get used to the quirks of the syntax in order to be able to generate all these really cool graphics or do all of these really cool statistical analyses. And so this is from ourproject.org, which is sort of the big umbrella site for the entire environment. Another thing that might be a little bit weird to get used to is that R itself is sort of self-contained data handling. So as opposed to Excel, where you can open data sets somewhere on your desktop and the data set stays on your desktop and you just sort of manipulate it. With R, you read data into R. And then it does a whole bunch of nice things in terms of data structures and reformatting things, depending on what kind of analysis you want to do. So we'll do a little bit of that today, just so you get a feel for it. It's got a whole set of operators for calculating on arrays. That's, in particular, matrices. We'll do some basic array calculations, just to give you a feel, again, for what the syntax is. And then a whole bunch of stuff for data analysis and graphics, and then the programming language itself. So those are the big components. So Mona mentioned that I used to work for a company called MathSoft. If you all know the history of the S language, so it was developed at Bell Labs in the late 80s. So that's the underlying language for both S+, and R. And so S+ was a commercial package that was built on the underlying S language. So it had graphical user interface and kind of interactive graphics and all of these kind of bells and whistles added on top of it. And R kind of simultaneously, in the early 2000s, R started taking off, I think, on an academic environment. And it was freely available, and there were enough people who were using S and S+, and they're like, okay. And Chambers, who was one of the guys who wrote S, was very much on board with the philosophy of having a freely available version of the language. So S+ has since been buried into all of these very proprietary software packages, and R has taken off. And so it's all very, very similar. There are quirks to each of the dialects. They like to call them different dialects. We probably won't see any of that today. Yes. All right, so this is from ourproject.org, and all of this is just to say that the website itself has a whole bunch of stuff down the side, including a bunch of documentation. And so I brought up a bunch of manuals that they have organized just like all of their software releases. They've got the release version, they've got a newly patched version, and they've got a development version that you can use if you're feeling crazy. And so the release for the documentation, the release versions are usually just fine. But this is all to say that you can get them in HTML or PDF. There's a very, very long history of user groups in S+, and R. So there's a lot of really good documentation available out there. And in particular, part of what we'll be doing in the basic workshop today is excerpted from this, an introduction to R. Okay, so RStudio, which I'm very glad to hear that you all have access to instances of it, because if you're going to dive into any kind of new software package that includes a programming language. I think having what's called an integrated development environment is a really nice way to do it. So it's got a bunch of stuff that you probably won't care about today. The thing that I think will come up a lot is that you can quickly jump to function definitions all from within, and you can get access to our help. Can you hear me?
Would you
No?
like a pointer?
That's okay. It's really not that big. I know. Yes, and my block.
Use the clicky fingers up on the drive.
Oh. That's all right. I'll stay active. It'll keep me awake. So yeah, the biggest thing for the purpose of today that's going to help you out using RStudio, the IDE, as opposed to just R, is that you're going to be able to type in commands, you're going to be able to see your commands, and you're also going to be able to bring up help files for any of the commands that you're looking at. So all of that's going to occur in one window, which is much, much, much nicer than having to keep track of a bunch of different windows being opened from your software package. If you've ever done that in Microsoft Word, and you have like separate help files open, and you have separate dialog boxes open, the IDE, so RStudio, allows you to just condense it all into one interface. And I think you all know what this looks like. If you were to open R, I don't know if any of you have opened R yet, you would see just this, so just the console. All right, so RStudio, you can set your preferences on how you actually want this to appear, but by default, this is what it looks like. And in particular, you can call up help files for any of the functions that you're working with down here in this lower pane by default.
Has everybody opened RStudio now? Should we?
It looks just like that. I just did.
Okay.
It looks just like
Thank
that,
you. I was like,
yes.
okay, just
Okay, Charla, can we just have a look at it now, or is it?
It's actually, so while everybody opens RStudio, then I'll hand out a worksheet, which as I mentioned, I sort of copied and pasted explanation and commands from an introduction to R, one of the online manuals. So I'll pass that out now while you all are opening it. We'll just do this.
We're doing this the next
All right, do that, sure.
Give it to us in electronic form, right?
What's that?
You will give it to us in electronic form, right?
I can. I just didn't know if you had access to a centralized. I can.
Yes.
Yeah.
Thank you.
Is anybody else into RStudio right now? Good. Great.
Oh, can we get one more?
All right. I think they are up there.
One more to.
Just one.
Is there a central location where I can upload these files just in case people like electronic versions better?
Yes. It's going onto the wiki. That's why
It's
she
going on
asked
the
you to
wiki?
put the presentation onto.
Okay. Okay.
These two. Yeah, definitely.
All right. So maybe on the break or something today, the 3 files that I'll be handing out today, I'll pass them off and they'll upload them to your wiki so you'll have electronic versions of them.
Yeah.
All right?
Yeah.
All right.
Did you want to
There we
use the
go.
pointer? This works nicely if you'd like.
So not right now because I think I'm going to be typing along.
Okay.
All right.
Does anybody need help with RStudio opening right now? Because we have Cornell and Mohammed to help us now, so, no. Okay, great.
All right. Okay. All right. So is that big enough? So between what you have and what's on the screen, and I'll be typing along. Okay. So what I'm going to do is I mainly gave this to you, one, so that you can follow along now, two, so that you have some written text to go along in case you try and look at this when you're back at your home institution and you're like, I have no idea what we tried to do with that command. So there's some written text with all of them. I will type a couple of extra commands just so for illustrative purposes that aren't in here. But for the most part, I'll be picking commands out of here. And like I said, yeah, the basic R workshop. And like I said, I put my name on it only so you'd remember where this is from. I didn't write any of this. It's basically a curated bits and pieces from that introduction to R manual that's available online. Okay. Okay, so the first section is vector creation and assignment. So when you're working with R, the biggest thing to understand is that every object that's stored in R has some sort of data type. And vectors are kind of the baseline level. And so it's always good to start with vectors and then extrapolate to something larger like a matrix, which is 2D vector, basically. So we'll do a lot of stuff initially with vectors, and it will also show you some of the arithmetic operations that are available in R that can operate on whole vectors, which are really nice.
Charla, I
Yeah.
don't know what a vector is still. I don't understand.
Okay.
Concept.
Okay, we will get there.
Okay.
Yeah.
Thanks.
Okay. So if the first thing, this first command there, which is x and then something or other, anything that is after a greater than sign. So basically this little greater than sign, anything that's after that in the file or the file I just gave you, means that what comes after that is something that you're supposed to type at the S+ prompt. Okay, so the first one that you see is that little greater than sign, and then it starts with x. All right, so x, and what that is less than dash, if anybody can tell that.
Yeah.
And then it looks like something like this. All right, C, parentheses.
Can I ask you something?
Yeah.
Do we need to have spaces? Do the spaces matter?
Oh, that's a good question. So around that little less than dash, that doesn't matter. It's good, what they call programming practice. If it helps you read it, then that's great. You don't have to have it, but if it helps you read it, then it's good practice, basically. Okay, so if everybody just types in that.
Ask a very quick
Yeah.
question. What is the difference between this like sign that you have there and just equal sign?
Yeah, we'll get there. Yeah, that's actually a really special sign in S+. And you're probably thinking of other just regular arithmetic operations or like an actual equal sign.
Because I've been using them interchangeably and that worked for me. So I'm wondering,
Yeah.
is there any situations when I shouldn't be using them interchangeably?
So that's one of those crazy remnants from S. So underlying S language could use them interchangeably. S+ and R actually moved away from using equal sign. So what she's asking about is this. So this little operator right here, which is less than equals, it's an assignment operator. It's basically saying, I'm going to create a variable named x, and I'm going to assign it everything I type after that. So what she is asking about is that she has often done this and just said x and equals. So let me see if I can. X and equals, and then anything that comes after it still gets assigned to the object x. So there are a lot of instances where you can use either. So what this is supposed to simulate is like a little arrow. And so it's, x gets everything after the arrow, or everything after the arrow gets put into x.
Makes sense.
Yeah, so the equal sign, because the equal sign gets used when we look up some of the functions, whenever you call a function and you set some of its arguments, so if you call plot, right, and you're plotting some x variable by some y variable. You can do x equals something and y equals something, and you can do that within the function. And so just to clarify that, they stopped using equal sign outside of functions. So I think it still works just for legacy purposes, but people have completely kind of gone away from it unless they started programming in this language when it was still S. And or if you learned from somebody who programmed when this was still S. All right?
I don't know why. Okay, thank you.
Okay, so all that's to say is that this less sign dash is a very, very special operator. It's called an assignment operator, and it's a way of defining a variable, in this case x, and assigning a bunch of values to that variable, which is going to be what we're going to type in, which is going to be a vector of 5 numbers. All right, so if you type that in, so it's C parentheses 10.4 comma, and you put commas in between each of the numbers, 5.6, 3.1, and so on. All right, so if you do that, one, you'll see up here in your environment, x is a numerical vector. It has 5 elements, and these are the elements. All right, so if you type x also, just by itself, then you'll see the same thing returned. All right, so whenever you define a variable and assign a bunch of stuff to it, whether it's a vector, whether it's a number, you can type that variable name by itself at the S+ prompt and see what's in it. Okay? So don't worry about this guy right now. That's just telling you it's a one-dimensional vector. It makes a lot more sense whenever you start looking at matrices. So at its simplest, a vector is kind of a list of elements, all the same. It could be a list of numbers. In this case, it's a list of 5 numbers. And the object itself is one thing, and that is the vector. And that's sort of like the base data structure that's in R. All right. You're like, that sounded really important.
It's like, sort of got it, you just heard it twice.
All right, so here, why don't we do this? Temp gets 3. All right, so I'm defining a variable named temp, and I'm assigning the value 3 to it. All right, so same thing. It shows up in our environment that we now have a variable named temp, and then if you type temp by itself, you get 3. All right, so temp, if you're just thinking about doing regular arithmetic, you're like, oh, temp is a number, it's 3. In R, it's actually a vector with one element in it. All right, so that's how it's defined. X, on the other hand, is a list of 5 elements. All of the elements happen to be numbers, and together that list is called a vector. All right, so you can have 2-dimensional vectors, which are just matrices. So 2-dimensional vectors, you basically have 2 coordinates for each element in that. So it's a little bit more complicated, but that's how the vector is sort of the base data structure, and then everything else is a much more complicated version of it. Does that make sense now?
Yeah.
Okay.
Yes, so the elements are not necessarily numbers, and right now I don't even know what else they could be, but in this case they are.
That's exactly right.
Okay.
Yep, so we'll talk a little bit about characters, so just little string variables, things like that. Yep. Okay, any questions so far? Okay. All right, so the other big thing to get out of this first section, vector creation and assignment, is just the idea that you can do a bunch of stuff and it cannot be saved. All right, so if we just did C 1, 2, 3, 4, 5, right? That's just like this command up here. We're creating some vector, it has 5 elements in it. We hit return. It's not actually assigned to any variable, so it's not saved in your environment. Okay, so the big thing is that this assignment operator here takes whatever you create and it puts it into a variable, so it saves it in your environment and you can actually see it up here. All right, so the example that they give here is 1 over x. So that is taking the reciprocal of each one of these 5 elements in a really, really quick shorthand kind of way. However, we didn't assign it to anything, so it's not saved. All right, so if we wanted to save it, we could do this, and we could rewrite over the variable temp that we already defined and say, I want that to be 1 over x now. And now it's changed up here in your environment. Okay? All right, so then the last thing, which we'll do just because they use it in an upcoming section, is to define the object y. And so you use the C function again, and you do x0, x. Okay, so C is a function, a very, very handy function. It's short for concatenate, if any of you have concatenated stuff in other languages. And so up here, we concatenated 5 numbers together and made it into 1 vector. Here, we're concatenating a vector of 5 elements plus the number 0 plus that same vector of 5 elements. So we're going to get out a vector of 11 elements. That's the hypothesis. All right, so y is now defined up here in your global environment. And if you type y, so 1, 2, 3, 4, 5. Here's your 0. 1, 2, 3, 4, 5. All right, so the function C is very handy. We'll use it a lot throughout the rest of this basic tutorial. So it's a way of, yeah, can all of you see that? Did all of you see that in your session? Mm-hmm. Okay. So C is very handy. It does a lot of stuff, and we'll use it a lot throughout. So at its you can think of it at its basic. It takes a number of things. So here it was 3 things. 2 of them were vectors, 1 of them was a number. Up here, 5 of them were numbers. It takes a number of things, concatenates them together, and outputs 1 vector.
Is there a limit to how many elements you can put in?
There's not a limit to how many elements. You can just keep on going. Most of the time, what happens with C is that you define some other function to spit out, say, 200 numbers or something like that, in order to, so that you don't have to type in those 200 numbers. So that's usually what happens. It's not, C isn't usually given a set of 200 things with commas in between them. Yeah.
You don't not want to type.
No, I don't think
Now,
many people would.
Can you put something like 1 to 25, and you would 1-25, and you would understand that as a series?
Close. We'll get to that. There's actually a section on that. It's close. The syntax is not quite like that, but it gets there.
I am not good at that.
Yes. Okay. So questions on this first section, just sort of getting used to vectors. Okay. All right, so we'll go on to the second section, which is vector arithmetic. Has anybody in here done anything in MATLAB before?
Has anybody used MATLAB before?
No.
No.
Not too many.
Okay. Only Bruce. So R and MATLAB and all of these other what we call sort of interpreted languages, which are built on top of things like C or C++, which are really grungy and much lower level. So they have these nice things built in where you can just operate very quickly on entire vectors of things, could be numbers. So we did that up here with the 1 over x. All right, so you normally think of the reciprocal as 1 over some number, right? This is actually 1 over a vector of numbers, and it operated on each element in that vector and took the reciprocal of each one and returned that. All right, so there's a whole bunch of other stuff that's built in that's made to operate on vectors and not just individual numbers. So that's what this second section is about. So the first command that they have you type is v gets 2 times x plus y plus 1. Okay, so this is a little crazy because what happens when you're working with vectors of different lengths is that the shorter vectors are always recycled. All right, so if this doesn't make sense here in this section, we're going to come back to it, and there'll be an illustration a little bit later that will make a little bit more sense. All right, so if you remember, x is a vector of 5, y is a vector of 11. So what this is going to do is say, all right, v is going to have to be a vector of 11. And it's going to be y all of the 11 elements in y plus 1, and then we've got to do something with this 2 times x. So x itself is only 5 elements, so it's going to go 2 times the 5 elements of x. Those will be your first 5 elements that are added on to y and 1. And then again, another 5 elements, and then the first 2 elements. All right, so it's totally crazy. We can do that on the board maybe during the break. So if you do this, so you get a warning message. Yes, you totally get a warning message because it's like, I don't know if you meant to do that. But then if you do that, then the simple arithmetic is that this is 2 times the first element of x plus the first element of y plus 1, 2 times the second element of x plus the second element of y plus 1, and so on. And then when you get to the 6th one, it's 2 times the first element of x plus the 6th element of y plus 1, and so on. All right? Does that make sense?
Yeah.
It's a little crazy.
But it does it.
But it totally does it. And it gives you a warning message just in case you didn't mean to do that. But it's a nice illustration to show that all this stuff is built in to operate on vectors, even if the vectors are different lengths. All right? So a couple of easier things to understand are all of these elementary arithmetic operators, which are on the next page of the workshop. So it's the usual ones, so plus, minus, multiplication, division, and then the little caret for raising to the power of. All right, so a little bit easier. If you remember, we've got x. We did 1 over x. You can do x plus 2 to add 2 to every element. You can do x minus 2 to subtract 2 from every element in x. You can do x times 2 to multiply every element in x by 2. You can do x divided by 2 to do the same thing. And you can do x caret, which is shift key 6, I think.
Yep.
Yeah, so shift 6 to get the little caret. It's the thing that's basically in the top of your number. And then you can do 2 to raise every element in x and square it. All right. And again, all of those, I just typed them in right here. Nothing got saved over here because I didn't assign any of them to some other variable, but you can if you wanted to save any of those. Right? I just typed x plus 2, so x is unchanged. It's still this vector over here. But what we spit out is every element of x plus 2. All right, and same thing with all of the rest of them. But you can save it. So say we wanted to write over temp again, and we wanted it to be the square of every element in x. Then when you look at temp, now that you've saved that, the fact that it's 5 elements long, just like x, but each of its elements are the square of the corresponding element in x. So the first element in x is 10.4, and 10.4 squared, I hope, is 108.16. The second element in x is 5.6, and that squared is 31.36.
That,
All right. Does everybody see that?
oh, okay, yes.
Yeah. Yes, and then the third element in x is 3.1. That squared is 9.61. Hopefully. I think it is.
Yeah.
Okay. So the next set of commands in this section are ways to get basic summary statistics for vectors of numbers. All right. So it mentions a number of them here. So one in particular is length. So length of the name of a variable that's a vector. So length of x is going to give you the number of elements that's in that variable. So what do you think this is going to return?
For which one? For the x?
Length of, yes. So it'll be 5. All right. But there are also a whole bunch of other ones just for, and so length is a built-in function. All of these arithmetic operators, plus, minus, multiplication, division, built-in operators in R. And then other functions that come standard with R are things like min. So given a vector of numbers, what's the minimum? So for x, the minimum is 3.1.
I don't understand that.
So if you look at the 5 elements here in x,
Yeah.
the smallest one, minimum,
Oh, the minimum
Yeah.
within the series.
Yep.
Okay,
the
yeah.
minimum within the vector is 3.1.
So if you do max,
If you do max,
it would be
Excellent.
21.7.
all right, what's your prediction?
21.7.
21.7. Yay!
Yay for me, I can do math.
You can get both of them at the same time using this function range. So that basically returns a vector with 2 elements. The first element is the minimum of what you pass to it, and the second element is the maximum of what you pass to it.
So if you wanted to give that a name, so then you would choose whatever you want to call it,
Mhm.
and the more than equal.
So
yeah,
yay
that
gets
arrow thing, yeah.
range x,
Okay.
all right? So if you do that, then yay gets saved over here. You can tell that it's of a vector, it's numeric with 2 elements. The first one, it does this automatically and calculates it for you. So in order to get here, it takes whatever you passed in, passes it on to the min function, and then returns that. So this is min x, and this is max x. Yeah?
Can you explain why you don't have to wrap that in the C function?
Yes. So if you take a look at, so the short answer is that range does that for you. So if you want to look at the code for range, it's actually in C. So if you were to look at sort of how the structure of the range function works, it would have an input argument, it would calculate what the minimum was, it would calculate the maximum, it would concatenate those two already into a vector, and it would return the vector back to you. And you can tell that you have that because when you do this, you end up with a one-dimensional vector. That's basically what this 1 means right here, and it has the 2 elements in it, and you can see that up here. So you know that it's not spitting out 2 separate numbers at you. It's already concatenated into 1 vector. That make sense?
So the one in the brackets is telling you it's one dimensional, and it's, number with the colon is telling you the number of dimensions is the first number, the number of elements is the second.
That's right.
Okay, and if you just type in a function without giving it a vector or an assignment after it, tells you something about that function that you know C, you may be able to understand.
So some of these functions aren't actually, a lot of the stuff that we're working with now is really, really baseline arithmetic stuff. And so what R is doing is writing a wrapper to something that does something really efficiently in C. But some of the other more complicated kind of statistical functions, so just like we can do this here, type out yay, it tells us what that yay object is. We can type out the name of a function, and it will tell us what it is. And it can be really useful if the function is actually written in R, or pieces of the function are written in R. And then you can see kind of the logic once you're all R experts and you're thinking and breathing and eating in R. Okay, so questions before we go on? Okay. So let's see, one of the other ones that I wanted to show you was summary. So summary X is really nice. This is a summary function for a vector of numbers, just like X. And so what it's written to do is just like range. So range went through, took whatever vector you gave it, calculated 2 things, minimum and maximum, and returned a vector with that. So what summary does is it takes a vector of numbers, and it calculates 5 different things. So the minimum, the first quartile, median, the mean, the third quartile, and the maximum, which is not very useful for a 5-element vector, but it might be much more useful for, say, a 200-element vector. Yeah. So that is summary. Much more sophisticated later on, there are summary functions for different object types. So this happens to be what summary returns whenever you give it a vector of just straight numbers. Is this 6 element, just full of your basic summary statistics. So your quartiles, min, maximum, mean, and median. All right, so other things that you can do is actually calculate the median on its own, or the mean and the median on its own. So there's built-in functions for that. There's other built-in functions that they mention here, like sum. So what do you think sum does when you give it a vector of numbers?
Add them up.
Adds them all up, yep. So those 5 numbers in X, you add them all up, it's 47.2, I hope. Pretty sure it is.
We're trustable.
Yes. So sum, mean, median, these are all built-in functions in R. If you wanted to define your own mean, you could do sum X over divided by length X. All right? So we're just taking a straight mean. You add up all of the elements, all 5 of the elements. You divide by the number of elements in there. That's a straight mean calculation, right? So we get the same thing as the mean function itself. Yes, exactly. I know. Yay, R is correct on its basic arithmetic. So if you like your variances, there's a built-in function for variance. And you can also calculate it yourself.
Is there something for standard deviation?
There is. So there's standard deviation. Standard dev, let me see, SD, I think. SD.
SD?
Yep. Yes, or, so I'll type in what they've given you there in the little workshop for how you calculate how variance is implemented. And I'll walk through it just because it's really useful as an illustration on how operators are prioritized whenever you have a really complicated expression. All right, so they have, for a variance calculation, if you just wanted to calculate it on your own. So you've got x minus mean x. All right, so sum x minus mean x squared. And then this is when spaces come in handy to make sure that
On this thing, they've got parentheses at the end of after the 2.
yeah. Yes, they're being very, very deliberate. I'm being much sloppier.
I don't know if you have to have it there, but
Yeah.
because usually you raise it, you have to raise the function first.
All right, let's make sure it works. 53.3, excellent. Okay,
Good.
so order of operations. This will come into play, I'll actually move this. This will come into play whenever you do anything a little bit more complicated than what we're doing now, but it's really standard both in R, like as a programming language, and then anything else that you might want to pick up. There's always an order of operations, so that it's kind of like in elementary school math where they say, oh, multiplication and division always comes before addition and subtraction, unless you put parentheses around something. So the same thing is true in programming languages. All right, so what we're doing here is, in the inside here, we've got the vector x minus the mean of x. So we're taking each element in that vector x, we're subtracting off the mean of the whole vector. All right, and then this parentheses and this parentheses is before this, and so it's taking that vector that comes out of that, x minus mean x, squaring all of those elements. All right, and then there, and then taking the sum of that. All right, so if anybody remembers their basic statistics, this is the numerator and how you calculate a sample variance. All right, and then that's divided by, we found out the length of x is 5 minus 1, and then that whole thing, because it's in separate parentheses, is in the denominator. Okay.
Obviously, that doesn't apply to variance, but let's say if you were doing vectors with different lengths, would you have the same sort of thing that happened when we did, what was it? X plus y? I think it was.
Yeah.
Yeah.
So if you try,
Reiterate the shorter one.
that's right. Yeah, so anytime you're trying to do something really complicated, even if you put lots of parentheses around them, what R is going to do is take the biggest vector, and then it's just going to recycle the smallest vectors according to how it knows what it's supposed to be doing with vector operations. Yep. So yeah, doesn't come into play here, but it would if you had
Yeah,
other
obviously it
vectors.
doesn't apply.
That's right.
Yeah. So, so if I was, so you did STDEV and that was incorrect. If I'm trying to figure out standard deviation and can't remember it's SD, is there a quick way to find that?
Yeah, that would actually be in
So,
help.
Yeah. I'm
Go for it.
help you in 1 second. So Brent has a fantastic cheat sheet he's going to share with us with all the commands, or whatever those are.
Okay, great.
But, yeah, but that, but there, if there's something that I'm looking for that's obscure, help, it's right there.
Yep.
Mhm.
Yep, so you want to go into the help, and I think, so you can standard
So you search.
deviation. Trying to figure out what, maybe this one, find and talk. Yeah, I think you can also do, like if you know one,
And then down at the bottom, it's stats double colon SD.
yeah. Da-da-da. Yeah, there are a number of ways to sort of make your way around the help system. So some of it, you know, especially when you're just starting from those lists of topics is really good. Other ways of doing it is getting to a function that's sort of close to what you want to do, because they always have see alsos. So this is,
So if you go to
yeah, this is the help page for variance.
you'll probably
Yep,
understand it.
and it gives you links to a whole bunch of other ones, and that's where it says SD for standard deviation. And it also gives you a bunch of examples at the bottom of each help file that you can type in and sort of play around with on your own to get the feel for what the syntax and what a particular function does. All right, no, that's a great question. You can tell that so STDEV is standard deviation in another language, and so it all starts to blend together after a while. Yes.
And that's the sort of thing that you forget very quickly if you don't use it every day.
Yeah.
Yeah, that's right.
But just knowing that there's a function for standard deviation and that you can find it, it's
Right.
like that's usually enough because
Yeah, no, that's great.
Yep.
It's right there.
So do they have like, I'm sorry, built-in function for most of the mathematical stuff like tangent and that sort of thing?
Yep. So that's we won't go through examples of that, but that's also they give you in this particular section they give you a whole bunch of other ones like log, exp, sine, cosine, tangent, square root. So exp is you can choose whatever your base is, and instead of using the caret, you can do base and exponent with the exp function. You can do log, same thing. You can choose the base, and you can do square root and things like that. If you wanted to do cube root, then you could do x caret 1/3. That's sort of the same thing. Everybody see that? All right, and so that's the cube root of x. All right, so yeah, the section here gives you a whole bunch of built-in ones that are likely very similar to the ones that are listed in those main topic pages, just to, again, get you started. So since we're talking about help, because we'll come back and look at help files a lot because it's really, really useful. So even once you become fluent in R, you'll have to look up what a particular function is, what its arguments are, what its defaults are, because it's going to be a lot more complicated than just these functions that we're playing around with right now that take a vector of numbers. And so this usage section in each of the help files will be how you can figure out how you can fiddle with the defaults, how you can set other arguments, how you can sort of customize how the function is called based on what you need. And so all we did in calculating calculating var right up here, so we gave it 1x, so one vector of numerics. There's all these other ones too. So there are all these other arguments that you can use. You can give it a second vector, and it does something special with that. You can tell it how to remove missing values if you want to. We'll talk about how missing values are stored in S+.
Charla, I missed how you got to the usage page.
So the usage page, so I'm just looking at the help file for variance.
On top of help.
Yep, so if you type var, which is the function that we use for variance over here, then it should bring up this one.
Okay.
And then all of the help files in R are structured very similarly. So it gives you a description of what the functions are that are in that page.
Great.
And then it gives you usage. It describes what the arguments are that you can pass to each one. It gives you special implementation details. It tells you what it returns.
Yes.
So this is where you would learn, for example, that the range function returns a vector of 2.
Yeah.
That would be given down here in the value section. References, this is very useful. I use this all the time, the see also section, so links out to other similar functions that you might want to look at in the help system.
Oh, it does give you standard deviation.
Yep, and that's exactly how I found. I was like, oh yeah, what is SD? I'll look up the variance help file and it'll tell me what the standard deviation function is. And then it has a whole bunch of examples at the bottom, which are useful for your own learning, that you can sort of type in and come up to speed with how a particular function's used. And the examples, especially a lot of these older ones, a lot of these examples for older built-in R functions, the examples are fantastic because they've gone through 10, 15 plus years of users and iterations. And so the examples are actually really helpful in coming up to speed with how a particular function's used and all the different things you can do with it. Okay. Other questions on that before? Okay, so I think the only other thing in this section was the sort function, which is useful. So if you look at x and you look at sort x, so x is a vector of 5. Sort x is those same 5 elements. They just happen to be sorted in a particular order. You know, could be useful. Yes, could be very useful. And there are lots of ways that you can sort it based on what the arguments are to the sort function. So you can sort it in descending order. You can do special things with alphanumeric characters, do different things with character strings than you do with numbers, things like that. But for what we're doing right now, just straight vectors of numbers, sort x, takes whatever you give it, sorts it in ascending numerical order, spits it back out. Okay.
Can you easily have it do it in the descending
Yep.
number?
Yeah. So you can look it up.
Okay.
Yep. So you can
I'll
look up the
practice.
exactly. So you can look up the help file. It will basically be giving it a different argument. So it will be something like this. This will be the help. Sort, comma, and then you'll give it another argument. And that other argument will tell the sort function, I want this in descending order, not ascending order, which is the default. Okay. Questions?
It's letters and numbers, or it wouldn't be.
For sort?
Yeah.
Yeah, it would be complicated.
Leave it at that.
Yeah, it would be complicated. So that would be digging into the help file just to make sure you know what the priority are. Does it sort the numbers first and then it sorts the letters? Yeah. Okay. So if there are no other questions, then we'll go on to So we'll go on to generating regular expressions, which gets at a little bit what you were asking about. So rather than, we typed in 5 elements in order to create the vector x. There's lots of shortcuts built in for generating what are called regular sequences of numbers. So for example, if you remember x, we typed those in by themselves. So what if I do this? Does that work? That doesn't work. I'm trying to I know. I was trying to figure out how to move it up. When I'm in Unix, I can just do clear, it goes to the top of the window. All right. Yes.
I think you could see.
I know, I was like,
Yeah, it's okay.
I can go down like this. Okay, so X, we typed those in. We used the C function to put them together, if you remember. All right, we can also do this. 1:30. What do you think that's going to return?
Numbers 1 to 30.
Numbers 1 through 30. All right, so super shorthand. 1:30, so the colon operator, when it's used like this, is very, very special. And so it's a quick way of generating basically sequences of integers. So 1 through 30 gives you 1, 2, 3, 4, yada, 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 all in up to 30. You can also do it in reverse order, 30 to 1.
How does it decide how many to put on one line?
It just depends on how wide your window is. Yeah. Yeah, that's just a display thing. It's not actually affecting how the numbers are stored at all. All right, so 30:1 is 30, 29, 28, da 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 da. So in descending order, for example. But there are a couple of functions which are,
Can I
yeah.
Why does it have 23 in brackets on the second line? This is, see
Yeah.
what I'm saying?
So this is, let me see.
Because
So
that's the rest of the
30,
of the-
29, 28, 27, 26, 25, 24, 23.
Oh,
so-
it's the position of that first
Yep.
number.
So 1 and 23, and when you're just returning objects, they're basically just sort of giving you a visual. Again, it doesn't actually affect how the data is stored.
Yeah, no, I know.
So if you do temp gets 30 to 1, right? So,
I
so
see.
temp up here,
Yeah, yeah,
it's a one-dimensional vector, has 30 elements in it, and that's what they are.
yeah, yeah.
But this is just a visual to help you sort of navigate when it spits everything out at the command line.
So another point for people who think very simply like me, if you stretch that window open and do it again, you won't get it like that.
That's right.
You
Let's
know,
see if we
it's
can
just
do
got
that.
more room.
Just the bracket just means.
But
it's
now
very
do
good.
it again and it's going to.
Yeah, it
it's
moves to
far enough.
28 now.
Yeah.
Okay, okay,
Yep.
okay, that makes sense.
Yeah, mine says 20.
Exactly.
Yeah.
All right. So we'll do nice 25 elements. So one thing, since we were just talking about order of operations, so if you do this, n gets, what is it? What did they tell us? 10. So we're going to define n to be the number 10, or a vector of length 1, and that's 10. So here's n. So to understand when parentheses come into play and how kind of high priority this colon operator is, if you do 1 to n minus 1, what do you think you'll get?
Okay, listen to this. N1 to n minus 1. You'll get.
10 minus 1.
Only 9.
Oh, you know, you need to put
Is it?
the parentheses with the n minus 1.
All right, let's do it this way first. What do you think you'll get?
You'll get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay, how did you get that?
Well, it's the series from 1 to 10, which is defined as 1 to 10 minus 1.
That's
for
right.
each number.
That's right. Yeah. So n is just 10. So this is saying colon, very high priority. So we're going to do that first because there are no parentheses here. We're going to do that first. So we're going to create the vector 1 to 10 first. And then we're going to have a vector of 10 elements, 1 to 10, and we're going to subtract 1 off of each of those. All right, and that's why we have 0 to 9 as what's output.
Well,
So if you put n minus 1 in parentheses, then it will give you 1 to 9.
Yes. If you do that, what do you think you're going to get?
1 to 9.
yeah.
Yeah. All right, does everybody see the difference?
Mm-hmm.
All right, so all of that's just saying that the colon's very, 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 very high priority. Unless you put parentheses specifically around stuff, it's going to do that first.
So
Before-
parentheses trump a colon.
Parentheses trump everything.
It's like in algebra.
Yeah, no,
Yeah.
it's not, no, it's not.
Yes. Okay, any other questions on that one? Okay, so there are two functions in this section, generating regular sequences, which are really, really nice. They come into play a lot whenever you're doing exploratory data analysis and you're generating plots. And so if you think of, if you make graphs in Excel and you have to come up with tick marks for the x-axis. So generating regular sequences in R is one quick and dirty way that you can do that. All right, and it's all encapsulated in the programming language. Okay, so the function seq, so why don't we look that up? SEQ. So if you look
That's sequence.
that is sequence, yes. Short for sequence, because we cannot have two syllables in any of these functions. Okay, so the seq function generates regular sequences, and there are a couple of different ways that you can use it. All right, this one, I'll just move this, and I will move the console over once we start typing again. But this one right here is kind of give you, it's very complicated, but it gives you all of your options that you'll probably use. And so the things to keep in track, the things to keep in mind is that seq, one argument you can give it is from, so the starting point that you're going to start your sequence at. By default, it's 1. So if you don't give a from, it's just going to set from equal to 1. 2 is the ending point. All right. By default, that's also 1. Not very helpful at all.
I was going to say,
Yeah.
that's not too long.
Yeah, it's interesting logic, how you set the defaults in all of these to kind of give you a lot of flexibility. Chances are, good programming practice, you're not going to say seq 2 equals 30, and then know that from is equal to 1, and have that be your command. Good programming practices, if you're going to use arguments, you're going to name your arguments, you're going to use all of them, and just because it's going to be much, much clearer whenever you go back and actually read what it is you wrote. So the argument from is where do you want to start your sequence. The argument to is where do you want to end your sequence of numbers. The argument by is what size step do you want to take in between the start and the end points. And again, it's got some crazy default. You can also, yes, you can also set the length instead.
Could you just use an integer for by?
You could if you're only using integers. You might want to use small step sizes if you're doing like from 1 to 4 by equals 0.25. So step sizes of 0.25 or something like that.
From divided by length out.
Yes.
Don't worry about it.
Yeah, don't worry about it. So another way, instead of setting what your step is, you can say, I want a sequence from 1 to 30, and I want 15 numbers in there. And that's what length.out will let you set. And then along's a little bit more sophisticated, so we might just do some examples then. Okay.
Length out is, so why is it set at null?
Length out,
Yeah.
because, again, that's sort of weird programming logic. If you set defaults for from, to, and by, you don't need length out.
Oh, null doesn't mean 0.
It's not 0.
Yeah.
Oh, okay.
Null just means like, yeah,
No
we're not
value.
gonna set it.
No value, okay.
Yep. All right, so
But if you forget to specify the, I suppose it will then default to the step.
all right, so if you remember, we just did 1 to 30, which were quick and dirty ways to generate sequences of integers in ascending order, or you could do 30 to 1. Quick and dirty ways to generate descending sequences of integers. You could do the same thing with seq. Seq 1, 30 by equals 1.
You have to write by?
I do, you should actually do this, from, to, and by.
So you should write everything.
At least at least initially.
You don't need to.
It's an equal between from.
Exactly. So this is saying, give me a sequence starting at 1. I want the sequence to end at 30, and I want the step size in between different elements to be 1. All right?
So in this case now you use the equal sign?
You use the equal sign. So this is what I sort of alluded to earlier today.
Because it's a function?
Yeah, so we talked, so a question was brought up earlier today, the difference between this little gets assignment operator versus using an equal sign in that place. All right, and so what I was saying is that you can use an equal sign here instead of this less than dash thing in order to take a variable or take some values and assign it to some variable. You can use an equal sign here instead of this guy. It's not anything, it was built into the underlying S language, so it's kind of a legacy thing. But because the equal sign are used in setting arguments to functions, then it's clearer whenever you're assigning values to variables to use this big assignment operator, and then the equal sign is reserved for setting argument values within a function. Does that make sense? That was sort of very circuitous. Okay. All right, so what we're doing here is from, so we're starting a sequence at 1, we're ending it at 30, and we're doing step sizes of 1. So this is the very, just like we calculated variance and compared it to what the built-in function was, this is basically a very long way of doing what we did up here with the colon operator. Okay, so we can do that. So it's the same thing. All right, so 1 colon 30 is a whole sequence. 26, 27, 28, 29, 30. In my display happen to be on a separate line. Same thing with this command, 1 through 30, and then 26 through 30 is on the second line. All right, so it's a very complicated, sort of language-intensive way of doing the same thing that we did with the colon.
What if, I'm trying to think.
All right, yeah. Sure. Is that better? Is that a little better? Okay.
Just for teaching purposes.
How did?
It's
Magic. It's magic.
Oh
right.
gosh, that's perfect.
Yeah. So on Macs, it's Apple Command and either plus or minus key.
Okay, what about what about the PC?
I know.
Do I just go to view? I suppose
I
I
know.
can just go to view and zoom.
I think it's Control on Windows. Control plus and minus.
Control plus.
Is it Control plus and minus on Windows?
It's Control plus plus, which
Okay.
makes sense, kind of.
Yeah. It should be the same thing that you use to increase or decrease, the shortcut that you use to increase or decrease the font size when you're in a browser. So if you're looking in a browser and the page is really small and you want to increase, you go to View, Increase, and there's like a little shortcut next to it.
Control plus, so that makes sense.
Huh?
Control plus.
Control plus plus. And I think decrease is Control plus minus.
Okay, that could be, makes sense, is the little thing at the bottom, that's sort of.
If you go in the view, it will tell you what the shortcut is.
From equals to, phi equals -1. All right, and so just to sort of close this out, so what we did here with the colon operator, we did a descending sequence, 30 to 1. You can do the same thing with the seq function. So from, we're starting at 30, we're going down to 1, and we're taking a step size of -1. So that's going 30, 29, 28, 27, 26. Okay? So that's just sort of getting you used to what the sequence function can do. But you can imagine you can put anything you want in for from, to, and by. And you can also set length instead of by. I mentioned that briefly. So down at the bottom of page 2, they give you 2 different ways of defining a pretty complicated sequence. So
S3 thing?
yep, S3 and S4. So S3 gets seq. So they did not name their arguments, but they're going from -5 0.25
With a step of minus.
with a step of 0.2. All right, so they're going from -5, -4.8, -4.6, -4.4, and so on. All right, and so if you assign that and then you look at it, that's what you get. All right, another way, if you happen to be working this way, is to set the length argument instead. So S4, they're going to define to be a sequence. So I'll do from equals 5 again, or from equals -5 again. By equals 0.2, and a total length of 51 elements.
So here it's obvious that if you specify what the arguments are, you don't have to put them in a specific order.
Exactly. Yeah, so I rearranged the arguments in this command from what they wrote here in the written thing, and so that's also a benefit of if you're futzing around with functions and you want to set different arguments. It's good programming practice to actually say argument gets value whenever you're calling it. One of the things that R allows you to do when you do that is that it doesn't matter what order you give the arguments in. So if you look at S4, they do seek, and then they set the length, and then they set the from, and then they set the by, which are not the order that they're in the help file, which is not the order that I'm typing them right here. But because we've named all of the arguments that we're setting values to, then you can put them in whatever order you want to.
But the default would be to, from, by, and then length.
That's right. And so this is just a different way.
Hmm?
Yeah, from, then to,
From, did I miss two?
I think I heard to, from, but whatever, it doesn't work.
Yeah, from, to, by.
Okay, so this S4 is just a slightly different way
And it
of
shows
getting
up
the
in
same vector.
alphabetical order in your values window.
Yeah,
It shows up in your values, that shows up in alphabetical order.
in the environment,
A global
Um,
environment,
yeah.
that's right.
yeah.
So here, so
Yeah,
oh,
it's
all of
not
these
that
guys,
order.
yes.
Yeah.
Yes, all of these guys, so the variables that you assign, they're just sorting it in sort of alphanumeric order up here. Yeah.
So can I just ask,
Sure.
once something is in the global environment,
Mhm.
that is going to be useful for something that we do later? Is that what happens?
That's right.
Okay.
So once something is in the global environment, so basically once you save something and it's there, you can sit here and type for like hours and hours and hours. And as long as you don't overwrite, so say we have n assigned to a value of 10,
Right.
all right? So that's in our global environment. If you don't assign n to anything else, when you call it later on, it's still going to be 10. Yep. And so kind of the next step after just sort of getting used to the interface is looking at your history and copying and pasting a bunch of commands into like a script and then being able to run sequences of commands. So we won't get to that today, but the global environment's actually really useful for that. Because you can do a whole bunch of exploratory stuff in the console. You can, type a whole bunch of crazy stuff. You can look at your environment, see what your variables are that you've defined, and as long as they're what you think they are and you haven't overwritten them, then you can still use them in subsequent commands.
So, some of those things that, you've got S3 has 51 elements in it. Is there an easy way to go back and see how you defined it?
Yeah, in the history.
Yeah. So that's what you get for the console. We haven't looked at the history, but
Oh, you can look at the history in the console to find that.
yeah. So a couple of
It
things.
seems like scrolling through everything in the console could take a while.
So there are a couple of shortcuts to get to commands that you
I
typed
see.
recently.
Yep, I see it.
You can do up arrow,
Mm-hmm.
which is handy.
Which were you doing now?
I'm doing the up arrow and the down arrow.
If you just keep hitting the up arrow, you go back up to the
Very
entire
handy.
floor.
Where?
Up arrow.
Just in
Yeah.
your, under your
Oh,
keyboard.
just
Yeah.
on the
Yeah.
keyboard.
Yep.
Okay.
So up arrow, when you're in the console and you're at the R prompt right there,
Right,
will sequentially go back through all of the commands you typed,
right.
which is
That
handy.
could get
Yeah,
very
it is really
long,
handy.
so going to the history and the environment might be.
Yeah, depending on what you want to do.
Depending on how far.
That's right. So S4 gets that, and then we did S3, and then S3 gets that, and so on. So I use the up arrows a lot whenever I type way too fast and I make mistakes, and there's all sorts of typos and stuff in it. So yeah, the up arrow is very handy, and then also looking in your history, which is one of the nice things that come out of RStudio that you don't actually get just looking at R.
Is there like a
Not that I know of. Not that, I'm sure somebody's written something, but not that I know of initially. That would be really handy. Okay.
You can search also both the environment and history, obviously.
Yeah, so you can search up here. Is that what you were thinking? Is that what you're asking? Yeah, from down here. Yeah, that I don't know. From up here, you have your catalog of like all of the commands that you typed, and you can search through it. But not anything I know from the prompt down here. Okay. Any other questions about the seq function?
Well,
Yes.
later in this, what if, sometimes you want to make a random sequence of numbers.
Yes. So we will actually get to one example. At the end of this.
That's fine.
Yeah, there's the plotting example at the very end. It generates 100 randomly distributed. And so that'll just give you at least a pointer into where all those functions are in S. Okay. Other questions? Okay, so the last function in this section is rep, which is also really, really handy for defining sequences. So at the top of page 3, they have S5. Oops. If you're in your S5 gets rep x times equal 5. Okay. Anybody want to take a wager on what?
Okay, what is it?
Yes, what that might return?
5 number series 5 times?
Yeah.
Yeah.
All right. So rep
X times.
takes whatever you give it. Could be a numeric vector. Could be just a single number, and it repeats it however many times, concatenates everything together automatically for you, and returns one object. All right. So if you look at S5. You can see 1, 2, 3, 4, 5, repeat, 1, 2, 3, 4, 5, and so on. Okay. The other way that they have right here to get you to used to using rep is with the each argument. So rep x each equals 5. Anybody want to take a wager on what that might return?
10.4, 10.4, 10.4, 10.4.
Are you a student?
I
know.
So.
He's like,
10.4, and then 5 times 5.6, and then 5 times 5.1, and 5
Yep.
times 6.1.
So this one takes the whole object and repeats it in whole 5 times. This one takes each element of that object and repeats it that many times. All right. So here's the first element of x, first. Second element of x, second, and so on.
Creating data sets, I guess,
Yeah.
data sets is good.
Yeah, you never know when you're going to use these. Like these are,
Oh, no,
yeah,
I'm happy to
super,
know that.
super fundamental functions, especially with graphics, just because if you're doing a lot of exploratory data analysis and you need to get a way to, access, say, certain elements of a particular data set that you're visualizing, then rep and seq are really easy ways in order to extract those. At a basic level, that's where they come in a lot. But then there's also, just sort of generating random data so that you can then go on and compare, for example.
And we're only working with one-dimensional strings.
Exactly.
Replicated and then working at 2 dimensions.
That's when it gets crazy.
Yeah, I can imagine.
Yep. Okay. So I think I was gonna see what time it is.
It's like 2:25.
Okay. So I think what I'll do is I'll finish just mentioning kind of logical values, missing values, character vectors, because those are other kinds of data types that you'll come into play with. On page 5, there's a whole example with read table that I think would take up a lot of time. So I think we'll skip that, and if anybody's interested, I can sort of give them the Reader's Digest version of what read table and its corresponding write table function does. We won't use those directly with RNA-Seq, but it's useful to go through it just to sort of get used to thinking of R as something where you read in data and the data is actually stored in R and not just located as a file out on your desktop. So read table and write table are really good functions for sort of getting used to that. But I think I'll skip over that example because I think it will take a very long time. So we'll just sort of go through the rest of the data types. And then before we break, at the end of page 6, there's a plotting example that will show you. You guys can go through each of the commands on your own just to see what graphics look like and also to see where they come up in RStudio. Okay. So logical vectors, very, very, very handy in any sort of programming language, certainly in R. And the logical operators are what they have listed. So it's less than or equal to, greater than or equal to, double equals for is equal to, question mark, and exclamation point equal to for not equal to. All right, so we'll go through each one of those. And what it does is if you're working with a vector, it takes each element in that vector, figures out what the logical operation is, and returns either true or false. So what you get out is a vector of the same size with a bunch of trues and falses in it. All right, so x greater than 13, for example. So here, we'll type x just so you see what x is again. All right, so if you do x greater than 13, what do you expect to see?
False, 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 true.
Yes. So the first 4 elements are definitely not greater than 13, but the last one is. All right. So that will give you kind of the reciprocal. You can also do greater than or equals to, and that's what the operator is. So it's the greater than sign with the equal sign, no space. That's very important with the operators, no space. Or you can do less than and equal to. All right, so that looks a little bit like the assignment operator, but it's got an equal sign instead of a dash. Very important to make the distinction. The double equal sign with no space between them is the, I hear is equal to question mark. So is x equal to 13? And so it goes through each element and tests whether it's exactly equal to 13. And none of them are equal to 13, so it returns a whole vector of falses. And then this one, so it's exclamation point equal sign. So that's R's way of saying not equal to. So x not equal to 13, what do you expect to see?
True.
Whole bunch of trues. Okay, so the logical operators, if you're using greater than or equal to, less than or equal to, is equal to question mark, or exclamation point equal sign for not equal to. There's no spaces in between the two characters, so that's very important. Otherwise, S plus is going to choke. R is going to choke. S plus would actually choke too, as would S.
We don't want that.
No.
Charla, is a true really a 1?
So true is a 1 in cases where things get coerced to numeric values. So in a lot of programming languages, you don't have this nice interface where a true is true in all capital letters and false is false. It's zeros and ones. And so in functions where logical values get coerced to numeric values, then yeah, they get coerced to 0 for false and 1 for true. Okay, questions? Okay, so just a couple more things and then we can set you loose on the little plotting example at the end. So missing values, because that's an integral part of anything that involves data. You will always have missing values. So what they, at the very, very bottom of page 3, so what they tell you to write is z gets this function. All right, so what do you think that's going to return?
What is NA? Not
See,
aware.
I think you have to compare, it's 1, 2, 3, what's that?
So NA is,
It's not available.
yeah, that's what you can think of it as. So NA is R's kind of abstraction of a missing value.
Oh, so 1, 3, since you're specifying 1 and 3, 2 has got to be missing.
So it's actually this vector, 1:3 is 1, 2, 3.
Yeah.
All right, and then you're concatenating that with this element in A. Okay, so this.
So it's not applying to the actual sequence.
No, so this C function is giving you a vector with 4 elements in it. The first 3 are created by this colon operator, 1, 2, 3. And then the fourth one stuck on the end is this NA. All right, so you've got 1, 2, 3, NA. Okay, so all of that is to say, was to basically get us a vector that had an NA in it. So NA is how R represents missing values. So if it was looking at this vector, it would see 1, 2, 3 blank.
So up in values, up until now, everything's been a number in one dimension with some number of elements. This
That's right.
is int instead of a number.
Yeah, it's kind of special. Yeah, are you looking up here in the environment?
I put
Yeah,
true
up
and it
there.
gave me a 1.
Yeah,
Yeah, so it's int
I know.
rather than a number because it's got something in it that's not a number.
exactly. So it's very, very grungy, low-level stuff that you're sort of getting into now, how this is represented. So what we could have done is z gets, z, I think this would change it. C 1.1, 1.1, 2.1, 3.1 NA.
Oh,
Yeah.
And now it thinks it's a number.
So yeah, this is very low-level stuff. So numeric is floating point, and that's how it's represented. Int is integer.
Oh, it's integer.
Yeah.
Okay.
So because you didn't actually specify what the data type was, it saw 3 integers, and it knew it had to do something because the NA was attached onto the end.
Right.
So it
okay.
did-
I didn't know what int was. It's
yeah,
integer. Which
integer.
Makes perfect sense.
Yep.
It's a kind of number.
Now, rather than putting NA, I put true,
Okay, what do you think that would do?
and it returned me a 1.
All right, so you did, okay.
I did 1, column 3, like you had, and then I put true rather than NA.
Okay, let's come back to that for a second. So let's finish just sort of explaining, and then we'll come back to typing in, yes, everything you learned today. So yeah, let me.
Sorry, I'm always trying to.
It's totally fine. I'm sure it'll come out to be a really, really interesting point. I just don't want to get derailed. Okay, so NAs. So C 1, 2, 3. So I've re-gone back to what the integers were. So this is a 4-element vector. It has 3 numbers at the beginning. It's got a missing value at the end. All right, so that was all just to get us to a point where we had a vector with a missing value in it. All right, so R has this function is.na. All right, and if you put in a vector, it's a logical function, and it will go through and test each element in what you give it and say, is this a missing value? I have no idea. All right, so the first 3 were not missing values. The fourth one was a missing value. Okay, so is.na is really, really handy for if you're looking at a giant data set and you don't know if when you imported it there was a bunch of missing values or not. This gives you a way of at least figuring out whether there are missing values and what your data set is.
So now
So when
it
you
returns
import it, it'll
false,
have
false,
that
false,
language
true.
in there.
So when you import it, which is not what we're going to go over, but there is something in read.table to say, how am I going to read in missing values? Basically, if you store them in Excel as a question mark, you can specify that your missing values are a question mark in this data set that you're reading in, and then R will convert it to an NA. Yep.
And also didn't seem case sensitive.
Um,
You did little NA and you have big NA.
no, so little NA and big NA, NA in general is one of those reserved things. So it doesn't want you to possibly write over what the missing value is. So it's reserved both uppercase, lowercase, all different combinations in between.
I'm sorry,
Yeah.
could you, on the, there's a line, Z, less than one. So you said, can you say what that means again?
Let's see,
You said
this one?
the right lower.
This one?
Yes.
All right, so what we're doing here, which is the command I think at the bottom of page 3. So we were working with X before, which was a vector. It had no missing numbers in it, right? No missing elements in it. They were all numeric values, filled up the whole vector. So we're creating a vector here that has a missing value in it. So what this is doing is it's returning a vector 1, 2, 3, because that's what the shorthand of the colon is. We can just put that inside the C function. And then this will actually take that 1, 2, 3 and tack on an NA at the end. So the way that R recognizes missing values is this NA thing. All right, so if you look at Z, you've got 1, 2, 3, and then the fourth element is missing, or NA. Okay? And then this is.NA function returns a logical, and it checks whether every single one of the elements in whatever you give it is missing, is a missing value, is an NA. All right, so 1 isn't missing, 2 isn't missing, 3 isn't missing, but the fourth element, NA, is missing, so it returns true there. Okay? Okay, yeah?
So instead of using Z, if I put NA, it should give me true.
So which,
Instead of using variable Z, just if I put NA, does it work?
so if you do,
No, is not, is dot no.
is.NA. What do you think that will return?
True.
Yeah. Yep. Vector, one element, because you only gave it one thing, happens to be missing.
You're saying just NA.
Yep.
Right, okay.
That's right.
Then it doesn't tell you about all the other ones in there.
Well,
That's
NA is not
really
a,
good.
NA is not a set, it's just
No, but
a single character.
Yeah, so all of this is doing is saying there is.NA sees a vector of length 1. It happens to be missing because it's NA. So it returns a vector of length 1 with true in it. That's all it's doing there.
So I think, just to go along with this, just say, is NA, and then put X in there. And
All
it
right.
should come up
False, false, false,
false,
false.
Good.
High false.
Is.NA X. That's right.
And I get, the reason this becomes important is because your diff out thing will have NAs in it.
Right.
There'll be lines where you won't have data, and this will help you deal with those down the road.
I completely missed the rationale. And what that state, what is it saying? Could you repeat?
Um,
Is that NA X? Dot NA.
Okay, so we'll do this one first. All right. So this one, if you remember, X was a vector of 5 elements, had 5 numbers in it.
Oh, okay.
Right?
I get it.
So that means there's no missing elements in X, which means it checks each one of them and it returns false for each of the elements. This one, all is.NA looks at is it says, all right, you're giving me a vector of 1 element, right? So that's what we're doing by inputting this thing that's reserved for missing values in R. So it sees a vector of 1, it's an NA, it's a missing value, so it's going to return a vector of 1 and it's going to say true. Okay. That clear?
Yeah, so obviously, again, the next logical step in the one you just described is to say is.NA, and then it says NA, then put a comma, and then put like a 1.
So you couldn't do that.
You can't do that.
I think you can't do that. The way that I would do it would be this.
Yeah, you have to put a C, sorry, I didn't, yeah.
Yep.
I see what you're saying,
Okay?
What is the rationale? What are you trying to ask?
So what we're doing here is we're actually defining what the vector is inside the call to is.NA. All All right, so we're creating a vector. It's got 2 elements in it. The first one's missing. The second one is the number 1. The C puts it together in a vector, and that vector is handed off to is.na. All right, so what do you think? What do you think it's going to return?
True, false.
True. All right, does everybody see that before I push the return? All right, so the only thing that's different here is that before we defined x, we said x gets this vector. Or we defined z gets this vector. And then we plugged in x for in is.na, or we plugged in z in is.na. So here, we're basically defining the vector on the fly.
Yeah.
All right? So the C just gives us a way to smash together a missing value and a 1 into a vector of size 2, and then that vector of size 2 is handed off to is.na.
Relative to, kind of real data, how are you using this?
Yeah.
Maybe we can get to that.
Yeah. What we're going to do today is basically like this very, very gentle introduction, and then we will leapfrog about 10 years in the future of, now that you're completely fluent in R, this is how you would analyze RNA-Seq data.
Yeah, and it's like the protocols that we've been working with, and
Yes.
then a miracle happened.
Exactly. So the purpose is in 3 hours not to give you sort of start and finish, like introduction to R, and now you understand everything about the syntax to be able to analyze your own RNA-Seq data. So it's to give you a little bit of fundamentals, and then to give you some practice, kind of how to access functions that will be useful for analyzing your RNA-Seq data and what it spits out, and gives you kind of enough tools to interpret it. But then you get to take all of this stuff and go home and practice a lot because that's all that's possible in 3 hours. Okay. All right, so questions on that now that you're all feeling very comfortable with missing values?
You got character values. Do we have character
Yep.
No,
So,
we have one more to do.
so character vectors, and then we'll take a break, and then you guys can go through the plotting example at the end at your own speed and see sort of what comes up. Okay? All right. So character vectors, all we've been working with right now are numeric, eagle eye, saw integer, and logical. But there's also character vectors, which comes into play a lot. Again, if you think about Excel and defining labels for your axes in plots. So you can do character vectors also. It depends on how you think about them. They're strings, they're stuff in quotation marks, they're not numbers, they don't allow for regular arithmetic operations like what you would do with plus and minus and things like that. Let's see. Oh, one more thing on missing values. So is.na, NA is different than numbers that don't exist. And so that is actually NaN, not a number. All right, so dividing.
1 divided by 0.
Yeah, dividing anything by 0 is going to give you not a number, and that is different and distinct from a missing value in NA. All right, so just something to keep in mind.
Also, when you have a spreadsheet, or when we get to, I guess, I don't remember what they call a spreadsheet type thing, but when you have a column of yes and no's or significant non-significant, that's going to come up NA.
That's right.
Yeah.
Yeah, it usually comes up whenever you are like doing arithmetic operations and you're just sort of abstracting it out so that you're dividing this column by this column, and that column happens to have some zeros in it, and so it blows up in certain elements, stuff like that. Okay, so character vectors. So the LABS command down at the bottom of page 4, this is what it says. So this is building up a lot of things that we've gone over to today. Okay, so paste, when you're working with character vectors, it's a really handy way of generating character vectors. In a lot of instances, you're going to read in your own data set, and you're going to have columns that happen to be strings or character vectors or however you want to refer to them. But the paste function, if you want to look it up, it's handy for generating, sort of automated generation of character vectors. So what it's doing, in its simplest form, you could say paste, let's see, X, Y, Z, A, B, C, put commas in between all of those strings, and it would paste together X, Y, A, Z, A, B, C. This is a little bit more complicated, just because, you know, it's the end of the exercise to make sure that everybody's juices are still running. So what it's doing is it's taking one vector, so 2 elements, an X and a Y. It's taking another vector, 1 through 10. It's going to paste them together with no space in between them. But
That's what equal is?
that's what this is right here. Separation. So you can do a space in between, or you can do a comma, or you can do a colon, depending on what you want to put in between elements of this vector and elements of this vector. All right, so for this one, sep equals, it's just quote, quote, with no space in between the quotes, saying I want nothing in between what I'm going to try and paste together. Okay, so harken back to sort of the beginning. This is a vector of 2, this is a vector of 10. What do you think is going to happen?
Paste them together?
If you try and paste them together, and you've got one vector of size 2, x, y, and one vector of size 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What did we learn before about operating with 2 vectors that are different sizes?
It's going to repeat the shortest one.
It's going to be repeat the shortest one, all right? So that's, if you do this, and then you do labs.
It didn't like it.
Okay, so if you parse it out, all right? So we've got a vector of 2 here, x and y. So we've got x, y, x, y, x, y, x, y, x, y. That vector is repeated 5 times. You've got the second vector here. It has 10 elements. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
I don't know why it's repeated 5 times.
Okay.
To equal the number of characters.
I know, it's crazy. Yeah, so what it's doing is it's saying, all right, I have to paste together a vector of 2 elements. I have to paste it with a vector of 10 elements. I'm going to start with a vector of 10 elements, and I'm just going to recycle the vector of 2 elements sequentially.
And if you have 11, does it end on X11?
It would end on X11, and it would not go to Y. That's right. And then the sep says, all right, we took this from here, we took the 1 from here, and there's nothing in between them. All right, if you did like a semicolon here, this would be X colon 1, Y colon 2, X colon 3, and so on. Okay, so it's another one of those kind of like seek, kind of like rep. Paste is a very, very handy function, especially when you're talking about graphics and sort of auto-generating character strings. It's worth looking at the help file, and it's worth going through some examples and just sort of playing around with it, because it is very handy for creating your character vectors. So the other thing to look at up here is that now we have a vector of size 10. These are the elements. The elements, because they're strings, they have quotes around them. And the CHR, as opposed to NUM, which is numeric or floating point, INT, which is integer, CHR is character string. So it lets you know that what you're looking at is a bunch of strings.
So it's not chromosome.
It's not chromosome. It looks like chromosome. It totally looks like chromosome.
Okay, now if I wanted to have x1, x2, x1, x2, y3, y4, x, would I put something like rep each 5? Would that work?
Yeah, we might have to walk through that one. And sort of, it would be some combination of paste and rep in there. So we could walk through it. Okay. So Mona, I don't know how long we want to take a break for, but I guess.
How much more do you think we will do?
I think the plotting example people can just sort of do on their own. It's nice, it's easy, it has random number generator. You can do it during the break. It's like super simple.
And then you're going to take us to anything else?
Then I can go through basics of bioconductor and RNA-Seq. I don't know that we'll get to them in depth, but again, it will, I'll give you the protocol paper that I'll be sort of pattern matching after, and you'll have access to the data. So even if we don't get to it now, you can download the data if it's completely different from what you're doing, and go through the commands. Okay?
So how long would that part take, so we know how long to take the break? Probably a while. Yeah.
Yeah, I mean, I think last summer, if you think this is crazy with a 3-hour workshop, he wrote up a 1.5-hour introduction to RNA-Seq using R for people who had never used R, and may or may not have seen what their actual RNA-Seq data looked like. And so, I know. So a lot of the example data files, which you can download and sort of play with, come from the curriculum that he put together. And then there's a little bit about where the data comes from. It's something that he's actually working on in zebrafish. So a lot of the curriculum from sort of the pattern matching with the Trapnell paper and the example data set come from Ben. Okay. So there's 2 other papers that if you haven't seen them, I think they're really, really, really helpful. And so one of them is this Garber et al. It's a Nature Methods review, if that sounds familiar. So core computational challenges in RNA-Seq analysis. So there's basically 3 steps that you want to do. You need to take all of your raw reads and you need to map them to something. You need to reconstruct with RNA-Seq reads in particular, your transcriptome. And then only the 3rd step is sort of visualization, expression quantification. And this 3rd step is where we're going to be at with R. So everything else, if you've used, I'll actually show in the next slide. The tuxedo workflow, that's what you all have been doing these 2 weeks. Okay. It's super fun because they have a little bow tie and they have a little top hat and it's very cute. Here are their little cufflinks. And then here's their cummerbund down here in R. So the tuxedo workflow is one analysis pipeline through RNA-Seq data. So bow tie, if you've used it, is just a short read aligner built for DNA sequence reads, not RNA-Seq. So top hat basically takes bow tie and then it accounts for the fact that you're actually looking at RNA-Seq and you can actually have spliced reads that are spliced together. If you're doing that with DNA sequence reads, you don't need to actually account for that, so top hat does that. Cufflinks is assembling, cuff compare, I don't know if you guys used that, comparing transcriptional assemblies to some annotation, cuff merge for 2 different replicates maybe that you're doing, but then cuff diff, I understand, is where you've gotten to. So coming up, analysis for differential expression. So after cuff diff, you have a whole bunch of different data files, and then cummerbund is the package in R that you can use to sort of visualize and analyze that. So the tuxedo workflow requires a fully sequenced reference genome. That's sort of the big thing. And the sequencing must be done using either Illumina or Solid. It's pretty standard. And I think you had some exposure to this working at the Unix and Linux command lines, or was that?
No.
Okay. So typically, any of the bioinformaticians that you might work with, they will cruise through top hat and cufflinks, and the end of the Trapnell paper is a whole bunch of Unix commands, not to be confused with R commands. So typically, top hat and cufflinks are, you type all of the commands at the Unix shell or the Linux shell if you happen to be working on a Mac. I'll just plant a seed here. It's possible to build really nice workflows for this that are visual through this thing called Galaxy. And so if any of you haven't used Galaxy, it's actually, I think it's really useful, especially if you're just getting used to sort of scripting. It gives you a way of saying, all right, here's my cuff diff. What are the inputs? What are the outputs? And it gives you a visual way of how all of your data goes through this workflow. Okay, so for the purpose of R, cummerbund is the thing at the end of that workflow. Something a little bit different, because I understand some of you were interested in knowing what RSEM EdgeR, and or I think DE-Seq was another one of the packages that people brought up. So the Trinity workflow, the big difference is that it doesn't require a fully sequenced reference genome. So it's for de novo, what's called de novo RNA-Seq, so that you're not doing RNA-Seq in humans, so you don't have a fully sequenced reference genome. You're doing RNA-Seq in some non-model organism, for example. So instead of taking all your short reads, mapping them to a known sequence reference genome, you take all of your short reads and you do all of this really complicated algorithmics to basically build back up what it is you're looking at.
How long does that take?
It depends. It depends on everything you would think.
Days?
So a lot of this stuff, especially the assembly, yeah, you collaborate with somebody who has access to a cluster. They help you sort of push it out and just let it go. So it depends on how many nodes you have on that and things like that. So the sequencing must also be done using Illumina machines. So RSEM, what it does is it uses bowtie, and it does this expectation maximization. So it's an iterative, which is a thing that can sort of take a very, very, very long time. An iterative way of kind of building up from short reads what your transcriptome actually is. A lot of this is also operated through Unix and Linux. EdgeR is an R package. And so again, the last step in this workflow is something that happens in R as a way to sort of visualize and analyze what's been going on. So EdgeR is one way of doing differential expression analysis in this. DE-Seq is another R package for doing the same thing. They just have different counting models underneath them. I can tell you a little bit more about how I understand those, but basically you can swap out EdgeR for DE-Seq here. So they're both packages that visualize and analyze the same kinds of data. They just have a different probability model underneath them.
Does they give you similar results? Are there situations when I want to use one versus another one?
Yeah, we can talk about that a little bit. I think EdgeR, yeah, I actually don't know the history of them. DE-Seq is supposed to be, more accurate, so modeling like the variance better, whereas EdgeR underestimates the variance in what you're looking at. But yeah, I think is that what you wanted to hear? I'm totally using DE-Seq.
That's what I'm using, so
Okay.
that's what I want to hear, yes.
Okay, so expression quantification metrics. There's a whole bunch of different ones. The examples from the Trapnell paper use two. But when coming up with expression quantification metrics, so if you're looking at how reads stack up in a particular piece of genome transcriptome, if you're looking how reads stack up, or if you're just counting reads and you're trying to come up with a proxy between that count and high or low expression level, there are two main sources of systematic variability that require normalization. All right, so one, longer transcripts will generate more reads. So more reads will map to longer transcripts than reads mapping to shorter transcripts. I'll show you a picture of this in a second. And the variability in the number of reads produced for each runs. So there might just be more reads produced in a particular run than in another run. So those are natural sources of variation that may or may not actually affect the expression level of a gene, but it can increase or decrease how your reads map up in a certain location. So any sort of metric has to normalize these two sources of systematic variability out. So things that you might have seen. Have you guys seen these metrics? Yeah. Okay, good. So RPKM, reads per kilobase of transcript per million mapped reads. So that normalizes a transcript's read by its length and by the number of mapped reads in the sample. And then FPKM is the same idea, only for paired-in reads, if you happen to be using paired-in libraries. So it's specifically for, it's the one that you see most because it's specifically for paired-in sequencing data, which is very useful. And so it accounts for the dependency between paired-in reads. So this is the one that you see the most. And then this is just a little visual from this review. So we've got 4 different cases here. All right, so we've got a sample where just the number of reads that were generated was very low. Same sample, and not same sample, but same structure where the number of reads generated was very high. Here you have short transcript with a medium number of reads generated, and here you have a longer transcript with a medium number of reads, but across the longer transcript, in absolute, there's more reads that pile up there. All right, so if you just go straight read count, this is what you'll see, and you'll say like, oh, 2 and 4, that means whatever those genes are must be expressed very highly. But once you normalize by the sources of variability, this guy sticks out, and 4 has been normalized for the length of the transcript. And then 1 in particular gets totally down counted in comparison. All right, does that give you a little bit of an intuition for what the metrics are? They just sort of fall out of a lot of the functions in Cumberbund, so I wanted to introduce them.
The length of the transcript, that's calculated from the gene model that you put in, from the genome reference that you provide?
I think it might be actually fragment length, like the, actually it's a good question, let me see. Yeah, I think it's the model. Yeah, I think you're right.
From the model then?
Yes.
Okay.
Yes.
So it's complicated if you have alternative splicing also?
Yes. Okay, so bioconductor. So how many people know what bioconductor is or have at least heard of bioconductor? All right. Heard of it. So bioconductor, so R has very energetic user communities. Bioinformatics is one of those energetic user communities. But there are also really energetic user communities around geosciences, around financial modeling, so in different disciplines. And each one of those have projects similar to bioconductor. So bioconductor is specifically bioinformatics with R. It's a big project to implement, test, package up a lot of very useful functions and exploratory graphs that bioinformaticians need a lot. And so this is just a description from our project. So provides access, facilitates integration, so that you're becoming an expert in R, you're like, I need a specific kind of heat map. So I'm going to write my own function for a heat map. And I'm going to have the axes just so, and it's going to take in this certain data type, and you have to do all this stuff ahead of time. Chances are, somebody already did it, uploaded it to Bioconductor, and you can just download a package and you start using the function immediately. Okay, so Bioconductor is very, very handy. If you have any experience in other programming languages where there are user-contributed packages or user-contributed libraries, Bioconductor is very similar, where a majority of what it does is through our packages that people contribute, test, try out, improve on, and then other people like you can go download the whole library and start using the functions in that library. And then this is just something, so it's open source. There's a release twice a year. Let's see, started in 2001. It is housed in Seattle, as all great software projects are housed. 2004 genome biology is when people started hearing about it a lot, and then most components are distributed as R packages. And then this is just a throwaway sentence. This functional scope of Bioconductor packages includes the analysis of DNA, microarray sequence, flow, SNP, and other data. You know, so everything, basically. So just like with R, I wanted to point you to this. This is actually from bioconductor.org, which is the main website for the project. And there's tons and tons of documentation inside of Bioconductor. So here we're looking at the page dedicated to Cumberbund, which we'll look at in just a second. So this is the end of the Tuxedo suite. and it has a whole bunch of stuff on it. For those of you who are using Edge R, for example, here's the page for Edge R. So there are user groups, documentation, tutorials, help files, all this stuff located online. And then once you install a particular library like Cumberbund, then all of the help files get downloaded into your R session, which we'll go through. Okay, so this is the data set that I was going to have you download. This is from zebrafish. So analyzing differential expression in genes during zebrafish embryogenesis. It just happens to be like a nice little project that Ben King, the lead instructor that I mentioned earlier, was working on. And so he put together this example data set for educational purposes. Okay, so references. This is the Tuxedo workflow, which is the paper that we just handed out, which is the one that you've been referring to, it sounds like, a lot these past 2 weeks. Trinity is described in this one relatively recently, just last year. And then this one is just, it's a very nice review. And it gives you some structure on what the 3 big steps are, the 3 big computational steps are in RNA-Seq. So it's a really nice review, has really nice kind of conceptual images.
Can I ask a quick question?
Yes.
If I'm working with mouse, which is very well documented. Is the Haas paper and the Trinity workflow something that's really going to be less useful for me than it is for those among us working with goats and bananas?
Yeah, so
Okay.
goats and bananas, exactly.
Goats, bananas, and bees. Yeah.
Yes.
We have the whole.
So trying to figure out where to put my time.
I would say
That's
tuxedo.
not it.
Yeah, I would say tuxedo. So Trinity is for non-model organisms. Mouse, definitely very well documented, certainly has a fully sequenced reference genome. So yeah, tuxedo, as long as all of your data is Illumina, then you're good. Yep.
What if you do other sequencing approach?
It's a good question.
Well, I don't understand, and that's probably just because I'm new to this whole thing, why it matters. Is it the kind of input files? Is that the reason?
So it's like the libraries that you input for particular chemistry, and then it's also biases in the chemistries. So a lot of work has gone into figuring out what Illumina is biased at, and so you can sort of correct for it, out the other end. So yeah, so I would say, I would take a look at this if you're working on something that's not Illumina data. But yeah, it's library construction, so basically what can you assume when you talk about kind of reconstructing a transcriptome, for example? So what are all the libraries that you input, and what are their structures, and then what are sort of the biases in each of the different chemistries? I know Tuxedo sort of the best of all of them, but if you're not using Illumina data, I'd take a look at that and see if they say anything in there. Okay, other questions?
I hope you did 9 in this one shot.
What's that?
I hope you did 9.
No, you'll actually have,
What to do?
yeah, you'll have all of these. So I will send,
Oh, you will.
I will send all of these to Mona, and she'll put them up on.
Yeah, you actually are, it's
right by your
right
elbow.
here.
Right
It's
there.
this thing.
That
These
too.
are Pictures of stuff that she printed out.
Is that already there?
Yeah.
Oh, you mean, and you
I
tell me
thought
that
you wanted
now?
I thought you wanted like a version on your phone. I thought you wanted a version on your phone for some, or on your iPad, so I thought there was a piece.
Yeah, actually,
You had some
that
graph
could be
out there.
useful, but she's going to send us the PowerPoint right now.
Yeah, both ways.
It just gets me from asking questions.
That's fine, no, it's good. We're both wondering.
Okay, so like I mentioned, the Cumberbund commands, the actual commands that I was going to have you do, were taken directly from page 572 of the Trapnel. There were a couple of things that, so instead of C1 and C2, this example data set had G1 and G2, so there were a couple of things that were a little bit different, but otherwise the commands were going to be kind of exactly the same. And so the only thing that I had left to sort of get you guys set up, which I think will actually be really useful, because it's not standard to, even once you get used to working in R, it's not standard to load in a library and start using the functions from a user-contributed library. So it's worth spending a little bit of time on that because you can go out and find all sorts of other libraries that might be useful for you. So the example data set, which you're more than welcome to go and download, it's a compressed tar file. Have you guys worked with compressed tar files at all? So it's gzipped, meaning, so basically a tar file takes a whole bunch of files, mashes them into one file. So it's a way to say, take all of the files in a directory, mash them into one file so that you only have to manipulate or move one file. And then gzip is just a utility for compressing the size of that, since a lot of these data files are enormous, as you can imagine. Putting them all together in one file ends up being enormous as well. So this is the name of a folder full of 21 data files, output from CUFDIF. This tells you that it's a tar collection, or tar file, a tar ball of those 21 files, and then gz, it tells you that that tar ball has then been compressed. So if you work on a Mac, you are in luck. Because Mac has Linux running underneath, so a lot of this stuff is automated. So what you can do is you can download this, you can double click it, it will unzip it, uncompress it, and it will create the folder and create the 21 files underneath it. All you have to do is double click it.
It's also really easy to do in discovery environments. There's a really easy app for it. So
Even better, even better.
It's called uncompress gunzip. Yeah, if you search
Yeah.
uncompressed GZ, you'll get it.
Yeah, yeah. So gunzip is also very useful.
So what about for those who works on, who does not work on?
So you just need like a WinZip utility. I think.
You have access to it from Atmosphere. From your Atmosphere instance, you can.
Oh, right.
Yeah, Atmosphere.
Yeah. Within Atmosphere, a little bit more. That's right.
Even better. Okay, so that was just getting the data. That's sort of step one. So step two was installing Bioconductor in your instance of R. So that's a little crazy. So let's not look at these guys first. All right. So the source command, the BioC-Lite, BioC-Lite cummerbund, and if you happen to be using EdgeR or DE-Seq, so EdgeR, BioC-Lite, EdgeR. Okay, so not looking at these two library commands. What these do is goes out, establishes a connection to the Bioconductor website that will allow you to start downloading Bioconductor. This installs Bioconductor. So this is all from either RStudio or the R prompt. So as long as you are connected, say, wirelessly, you can run this source command, which has this URL in it. So this establishes the connection to Bioconductor. This installs Bioconductor, the light version, locally on your instance of R. This installs the library cummerbund. This installs the library EdgeR. All right. Questions on that?
Just, so this is all taking place on an instance in Atmosphere, not on our laptop because this stuff is too big.
It actually can take place on your laptop. So it's for the example data set, at least, if you wanted to sort of, get your feet wet with the example data set, you can do it all on your laptop. So the data files, are big, but they're not going to take down your local wireless network or anything like that. This here can absolutely be done on your local laptop, just because this is just a bunch of functions. You're just basically installing a bunch of functions in your version of R. And so that's not going to, again, that's not going to take down your wireless. It's not going to suck up all the memory or anything like that.
But using those functions on my data files might.
Maybe. It depends on what kind of Mac you have. Yeah, the Macs are sort of surprisingly, can handle it. I mean, some things, I would say not necessarily with the R stuff, but with a lot of the other stuff that led up to you coming into R, That's going to be the stuff that's going to be most computationally intensive. The R stuff is, once you read a data set in, then you can kind of traipse through and create files and stuff like that pretty easily. Yeah.
So I think I'm right when I say this. I think I discovered this kind of on my own, but the first three commands that you're writing there, once you've done that with your present version of R, you don't have to do that again.
Exactly.
You do a new version of R. Oh, does it say that?
Exactly.
Sorry, she just read.
So no, that's why I was covering up these guys. So installing bioconductor and installing particular libraries of packages, like Cummerbund and EdgeR, you can do that on your local instance. You can do that once. It's just like installing a new software package on your laptop. You don't have to do that again. What you do have to do again is load those libraries into your session. All right, so this library command basically says, all right, I installed Cummerbund. It's somewhere here in my installation of R. I just need to load all of the functions into my current session. So this library command loads all the functions in Cummerbund in your current session. This library command loads all of the functions in the EdgeR package in your current session. If you close R and you open it back up, you'll have to rerun these. Just the library commands, not the installation commands. All right, does that make sense? Okay. And the other thing is that once you run these library commands, so after you've installed a particular bioconductor package and you've loaded it into your current session, all of the help files for the functions in that package will be available just like all of the help files for the built-in R functions. All right, but you have to load the library up in order to be able to access them in the same way as the help files for all of the built-in functions. Okay. Okay, so the other thing that's kind of useful, which would come into play just so that you don't have to type up a whole bunch of stuff, is changing the default working directory. I don't know if you guys had to deal with this at all. So say you need to read in a data file, and a data file is located in C, program files, user, username, NSF working group, DNALC, blah, 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 blah. So it's located in some crazy nested folder, and you don't want to have to keep typing that. You just want to be able to set that folder to be your working directory. So anything you read in is going to look in that folder by default. Anything you write out, any data you generate, any figures or graphics you generate are going to be put in that directory by default. So that's the idea of a working directory in RStudio. So this is where it is in RStudio. It's a little bit different depending on if you're just looking at R, where it's located. So you can go to Tools, Global Options, and then you can, this is for specifically the Cummerbund commands in Trapnel. So you want to set the working directory to the folder that contains all the data files. I'll show you what I mean there in a second. But yeah, so the changing the working directory just makes your life a little bit easier. If you want to keep everything in this session, anything that you read in or write out or any graphics you create in one folder, that's what the working directory does. All right. Okay, so I'll show you just to sort of go through. So this is my desktop on my Mac. This is the tar.gz file with the example data in it. So I downloaded it, I double-clicked it, it created this folder, and then underneath that folder is all 21 data files. So you can see, like they're decently sized, but they're not giant, right? The big tard file is the biggest, it's 41 megs. But all of the rest of them, especially by today's laptop standards, not giant. You can actually do pretty decent manipulation with them without worrying that you're gonna burn through all of your memory. So these are all of the 21 files, and then what I just mentioned with the working directory. In order to make the commands work as is in the back of the Tracnol protocol, I would set my working directory to desktop, because it is the directory that contains the folder that contains the data file. A little weird. It's a little bit strange. But that will basically allow you to do everything as is in the Tracnol protocol. Okay, so questions?
Do you want us to do this by tomorrow?
Yeah, you can if you want. I won't be here to check. I won't be here to check
I
on
don't know
you.
whether you want to start from tomorrow or, you know.
Yeah, so I think what I'll do with the rest of the time is,
So all the files in there, can you show it really quick?
Yeah.
Because I have the Cuptip out on mine for my thing. I just want to see if I have the same group of things. Placing transfers, TSS. Okay.
yeah.
Does that have the database file out of it?
So the stuff we get out of DNA Subway will have a if you can download the whole folder onto your atmosphere, it'll have a very similar list.
That's good.
Yeah.
That's great. Do you get 21 files out of CuffDiff on DNA Subway? That's the thing that I don't know. This might have,
I gotta count them, I'll tell you in a second.
yeah, this might have one or two crazy things in it.
Subway has less coming out of it. I think we looked at it, somebody looked at it with me, I think it was 13 or something.
13 or something.
But the discovery environment is 25, I think, right now.
I have 29.
29, excellent.
Yeah.
Yeah, sorry.
All right. Well, there may be something with the data that you get out of DNA Subway. You might have to modify this a little bit.
A lot of them look the same. I just
Yeah.
looked at it very quickly.
Yeah, exactly. Okay, so I think what I'll do, just with the last couple of minutes, is I'll just go through the 6 or 7 commands here, and I'll go through the bioconductor installation. So basically, go through the bioconductor installation, cummerbund installation, loading it in, changing the working directory, and then going through these 6 or 7 commands here in Tracnol, just so you have something that you can sort of see if you're going to go through and try this on your own. All right, so I'll go back to all right. Can I take these for a second?
Yes.
Just to make sure I have. Okay. So I will. All right. Is that big enough for everybody to see in the back? All right. So I'll start with the source command. All right, so apparently I already installed it. All right, so BioC Lite. So it's downloading a bunch of stuff for bioconductor in my version of R. So, yeah, so I will update all, just to start from scratch. Anybody know any good jokes?
Can I just re-borrow it?
Yes?
Thank you. That's what's not a good joke.
Okay, so bioconductor is now in my instance. All right, so just a reminder, I did the source code. I did the source command. I did the BioC Lite command. So now I can do cummerbund. So if you notice, it's in quotes. So BioC Lite accepts a character string of something that it's going to go and try and look for the name of a library. All right, so it's in quotes. The thing to know is that it's totally case sensitive. Maybe it's not. Yes, perhaps you meant cummerbund. It's going to suggest, like, yes, it's going to suggest that you actually meant capital R there. Yes.
So nice.
Very nice.
I think it should be
know.
talking back to you, not just telling you.
All right, and then EdgeR, if you want to install EdgeR. Okay, so now the packages and bioconductor are installed. I don't have to ever do that again with this installation of R and RStudio, but I do need to load them both.
Right at the end, it said something about installed directories are just not writable for a few of them, cannot update. It gave me a list of gviz, there's a few of them that it couldn't update. Is that normal?
I think it depends on maybe how you're, is that a university laptop or is that your own laptop?
No, she's doing
It's my
atmosphere.
Oh, you're doing Atmosphere.
Yeah.
Oh, okay. That might be it. It might be like central directories or something that is part of the instance.
I'm doing it in parallel on my own end.
Okay.
You didn't ask the question, update also.
I got a lot less.
So I did all, and it worked out fine on my laptop. It might, if you're using Atmosphere, it might not actually let you update everything. Okay, then yeah, you can do all.
I only had two that wouldn't, there was this much smaller list, so. And then
All right, so loading in the library for Cummerbund, again, case sensitive. So if you miss the capital R, it's going to say, I have no idea what you're talking about. And it won't actually suggest that there's something else. So it's case sensitive. And it's not a quotation, exactly. All right, and then just for kicks, you can do EdgeR. And then once you do that, one of the commands that we will use is read cuff. All right.
Oh.
So read cufflinks is one of the first commands in this Trapnel protocol. It is a function. It's available only in Cummerbund.
Just go from here.
Yeah, yep, I'm just going down there. It's available through Cummerbund. Once you load Cummerbund in using the library command, all of its help files are available here. So you can look up read cufflinks if you want to. And it's a whole bunch of complicated stuff, which you can take a look at. But all of that is to say that once you load a library, then you can access all of the help files for the functions in that library just from here, just like you would any of the built-in functions. Okay, so for those of you who are following along, trying, yes. If you want to type along, feel free. There's just a couple of commands here. If you want to just watch and sort of see what happens, and then maybe do it tomorrow, or do it kind of on your own time when you have more time to sift through and think about what all the functions are, that's fine too. So I just loaded the library, or I just called the library command on page 572.
The DNA subway name is cuffdiff underscore out. You downloaded your DNA subway output onto your Atmosphere instead of, it's written here as just diff underscore out, but ours is cuffdiff
Okay.
underscore out.
So the other thing that I was going to show you is just changing working directory. So I think I did preferences. So default working directory when not in a project, I'm going to set to my desktop. All right, so that just means anything that I generate in this session is going to be written to or read by default from the desktop. But because that's where this diff.out folder, diff underscore out folder is for me, that'll just make it a little bit easier for the rest of these commands. All right, so okay. Okay, so cuff. I'm going to do cuff.data just because I don't like using underscores in names. So cuff.data gets read cufflinks. And then this is the, what did I actually call it? TGAC underscore July 13 underscore diff underscore out. That's,
So did you have to give it a pathway to get to that file?
I didn't because I changed my working directory.
But you could give the full path.
You can give the full path. So here I'm going to do
So if
this.
you're on your Atmosphere desktop, what would be the full path?
Desktop slash copy from small.
Say it again? Backslash?
Desktop,
Uh-huh.
capital D. If you haven't changed your.
I haven't, it's just on the desktop. Yeah.
And then slash copy underscore out.
Got it.
All right, so here's cuff data, read cuff links. This is the name of the folder where all of my data is stored. My working directory is desktop. This folder is located directly underneath my desktop, so I don't have to do desktop dash whatever. So I don't have to give it a full path name. That's what changing your working directory actually gets you. So what it's going to do is it's going to search in that folder for a whole bunch of files in order to build a cufflinks database within R with all of its regular data structures. Oh, shoot. Did I spell this right? TGAC underscore July underscore diff underscore out. Darn it. Wonder if I do have to do desktop.
Desktop has to be a capital D for it to work, if you guys are trying to figure it out.
Yeah.
Does it has to be DNALC?
Ugh, yeah, so apparently my working directory didn't take. Darn it. So I did have to give it a path. All right, so it's doing a bunch of stuff to the cufflinks data so that it's doing a whole bunch of stuff.
At this point, is it building a database?
Yeah. It's building a database specifically and
Sharing each of those files.
and building it in a bunch of different ways that R can access. So it's a lot of reformatting, and you can see reshaping. So making it into something that R actually can.
That has to be unzipped already.
It does have to be unzipped. Yep. So it has to be an
Do you get
unzipped
all
folder
of
of all.
them, or, because I like downloaded, just on my laptop, I downloaded geneexp.diff and isoforms.underscore
Yeah.
ex. And someone said, do I need all the files, or could I just do it with those two?
It's a good question. I think in order to do read cufflinks, which
Uh-huh.
allows you to manipulate the data and extract it and stuff like that, then you do need all of the data.
Yeah, because the way the download works is you have to do each file individually.
Awesome.
All download, because I get a Java error.
So I'm confused looking at like our cuff diff data, what the equivalent file that has this information
Yeah. So did you figure it out? Desktop dash.
Did you, using iDrop, did you bring your
I was
cuff diff
able to bring
out
my whole
to your desktop?
Yes.
Right, so
I've
then
got
you're
like
gonna
29
go
files
in this paper right here, where it
Uh-huh.
says, you're gonna write it here, instead of doing diff underscore out, you're gonna go desktop with capital D,
Oh, that whole folder,
underscore cuff diff out.
it's that folder, it's not a file.
You're putting a whole folder in,
Okay,
okay? Yeah.
okay,
Yeah.
okay.
Charles, just a little check that we have routines coming in before.
Okay. Okay.
Yeah, I was trying to do this
Too much good stuff.
just on my computer, and I realized that all the files are nothing here.
It is a crazy hour. Yeah, well, this was supposed to be like doing stuff. Yeah.
So that file that you have that has all the data that we're going to use, I downloaded it, but
Tonight? Oh.
because it's that zip read,
It's gonna be super general, just not.
how do I go from there?
Yeah, look at the title.
Career,
Yeah.
putting
Yeah.
where do I need to put it? Because
I know.
currently
Look
I'm
at the title.
I just started
Apparently not. I think maybe you have to set it and like set a project or something like that. Yeah.
So now it's downloaded here.
Judy, can you show me what you wrote down?
Yeah.
Judy has to share that with
All right.
With the inside the scene?
Yeah. So
Let her continue, please, now. Judy,
Inside the single
please.
quote.
That's the R C.
All right, so since we're short on time, I will basically show you I'll show you an expression bar plot, the analog for this data set, so that if you're looking along, you can get a graph like, what is that, figure 9A on page 574. And so it's down in step 12. So I'll just show you this so that you're oriented a little bit to kind of how this works whenever you're using Cummerbund. So what they had is my gene gets get gene. So get gene is something that's written specifically for CuffDiff data in Cummerbund. So it's a get gene function in Cummerbund. And so cuff data is what we just created by calling the read cufflinks function. And then the only difference is that in the paper, their gene name is something, Rigusa Shisha. And in the example data set, one gene name is called STAT3. Okay.
Oh, so we did gene name.
Yep, so it's the gene name.
Oh, okay.
Yeah, which
Some gene name.
some gene name that's in the data set. All right, so this is the name of a gene that's in your CuffDiff data set. This is the cufflinks data that you just created using read cufflinks. GetGene is a function in Cummerbund that allows you to pass in that huge cufflinks database and get a gene out with all of its attributes. And we're assigning it to some variable called myGene. And then once you do that, did I type that in wrong? What did I do? Oh, that's right. I decided to not call it cuff underscore data. I called it cuff dot data. So I did that just because I don't like underscores in names. Okay. So now it's reading in all of the attributes for the STAT3 gene as it's formatted in this cufflinks database, and then expression bar plot on this myGene thing. Expression bar plot, again, a function, graphics function available in Cummerbund. So once you do that, your plot comes up here. Let's see if I can. All right, so some sample name, gene 1, gene 2, FPKM. So here's your FPKM measure. So expression bar plot gives you a bar plot. I wonder, this doesn't look right, actually. I think it's supposed to be much prettier than this. It's supposed to actually...
Is that the command that you gave?
It's supposed to look like this. Did I do expression bar plot?
Yeah, do you mean box plot?
I do, I think. No, bar plot, I think. Yeah, I do mean bar. Yes, it's supposed to look much prettier. This is what it's supposed to look like. So, yeah, it's a way of visualizing the FPKM values for different genes that you're looking at.
You sometimes lose the little carrot thing, and like all of a sudden I lost my little carrot, so I can't.
The carrot thing?
It's probably the little.
Do you have a stop
I
sign?
am lying.
It's
Probably
working.
doing something.
Oh, yeah.
I think it's still cranking.
It's thinking hard.
All right.
Yes, it's thinking hard. Okay. So I will stop there since somebody else is coming in at 4. But since you all have the Trapnel file.
These commands are the ones that will, okay.
Yeah. And I can actually send Mona an email with the exact commands that should work on the example data files. But it might be easier for you guys if you've already been working in DNA Subway to sort of kind of traipse through based on what your data set is. But the 6 or 7 commands on page 572 here will give you a really good introduction to what's available in Cummerbund in terms of analyzing what your CuffDiff data is. And then I will give Mona electronic versions of this basic workshop, and then electronic version also of my slides. And if you guys have any questions, feel free.
All right, thank you so
Sure.
much. That was fantastic. But we want you